Okay students, in this video we are going to speak about the electric field intensity due to a solid non-conducting sphere. Solid non-conducting sphere, for which let us assume that this is our solid non-conducting sphere. The peculiarity of a solid non-conducting sphere is that if we are giving a charge over to the sphere, that charge will be uniformly distributed throughout the volume of the conducting sphere. That is, it will be uniformly distributed completely inside the sphere at every space. You know what will happen to the charge if we are giving it to a solid conducting sphere. Now this is our non-conducting sphere. If we are giving a charge to a conducting sphere or a spherical shell, that charge will be getting accumulated over the surface. But since this is a non-conducting solid sphere, the charge is not accumulated over the surface. It is uniformly distributed throughout the sphere. Okay. Then let us assume that the radius of this sphere is capital R. Capital R is the radius of this sphere. And we have to find out the electric field intensity due to this solid non-conducting sphere, for which let's initially find out the electric field intensity inside the sphere. Let me define a point A which is inside the sphere, and this point A is at a distance, let us say small r, from the center. It is at a distance small r from the center. Our task is to find out the electric field intensity at this point. For finding out the electric field intensity, we are solving it as the application of Gauss law. What is Gauss law? Integral of E dot ds, that is equal to q enclosed by epsilon 0. Integral of E dot ds, that is equal to q enclosed by epsilon 0. This is our Gauss law. Okay. Therefore, if we are using Gauss law in this particular situation, let's understand about the volume charge density. Before speaking about Gauss law, before proceeding in this equation, let's understand what is volume charge density. Volume charge density is rho. It is charge per unit volume. Therefore, let us assume that the total charge that is accumulated over this sphere is Q. Q is the total charge on this or throughout accumulated on this sphere. Therefore, the volume charge density rho, it will be charge per unit volume, that is Q divided by volume of the sphere. We could write it as 4 by 3 pi capital RQ, since the charge is distributed over this capital R radius. Therefore, we could write 3Q divided by 4 pi RQ. This is the volume charge density. Okay. Then the advantage of volume charge density is we could find out the charge in any volume with the help of volume charge density. How can we find out the charge in any volume? For an example, you just look over here. In this case, in our current circumstance, we have to find out the charge accumulated on the smaller radius portion. Why? If we are using Gauss law, we will have to assume a Gaussian surface, and the Gaussian surface that we are assuming in this case is a sphere of radius r. Then what is Q enclosed? Q enclosed is the charge inside this blue sphere. Charge inside this blue sphere. How can we find out the charge inside this blue sphere? It is very simple. That is, if we know charge density, that is charge per unit volume, charge density into volume of this blue portion will give you Q enclosed or Q inside this blue region. What is rho is rho itself? What is volume of this blue color circle or blue color sphere? It's not circle, it is sphere. Blue color sphere, it will be 4 by 3 pi small r cube. Since we are saying about the volume of the smaller sphere, rho into 4 by 3 pi small r cube. Okay, then Q enclosed is rho into 4 by 3 pi small r cube. Let us substitute for rho, that is, as we know, rho is 3q divided by 4 pi r cube. Therefore, if we are substituting for this rho, we could write 3q divided by 4 pi capital R cube into what? Into the remaining portion, that is 4 by 3 pi small r cube. Then we could clearly cancel this 4 pi, 4 pi, 3, 3. Then it will be, that is Q enclosed will be R cube Q divided by capital R cube. Okay, therefore this is our Q enclosed. Then let's use it in this equation, that is integral of E dot ds, that is equal to Q enclosed by epsilon 0. It could be rewritten as integral of E ds, that is equal to Q enclosed by epsilon 0, in which, since E is a constant, we can take E out. E into integral of ds, that is equal to 1 by epsilon 0 Q. Q enclosed. What is Q enclosed? Let's replace Q enclosed as R cube Q divided by R cube, that is small r cube Q divided by capital R cube. Okay, capital R cube. Therefore, we are getting an equation like this, and from this, what is integral of ds? Integral of ds is the total area of the Gaussian surface. Total area of the Gaussian surface. The radius of Gaussian surface is small r. The radius of the Gaussian surface is the blue color sphere, that is small r. Therefore, integral of ds, it should be total surface area of the small r radius sphere, that is 4 pi small r square. 4 pi r square, 4 pi small r square. Therefore, E into integral of ds, it is 4 pi small r square, that is equal to r cube Q divided by epsilon 0 r cube. Then we will get E is equal to, we could take this 4 pi r square to the other side. Then before taking 4 pi r square to the other side, we could cancel this r square and r cube and write an r over here. Then we will get r cube divided by 4 pi epsilon 0 r cube, that is rewritten as 1 by 4 pi epsilon 0 QR divided by capital R cube. Therefore, this is the expression for electric field intensity inside the Gaussian surface or inside the sphere. Electric field intensity inside the non-conducting solid sphere is 1 by 4 pi epsilon 0 QR divided by R cube. Then let's say, what is the electric field intensity outside? Or let's say electric field intensity on the surface. As the next step, let me write what will be electric field intensity on the surface. In order to say about electric field intensity on the surface, let us start from Gauss law, that is integral of E dot ds, that is equal to Q enclosed by epsilon 0. Then we could write it as integral of E ds, that is equal to Q enclosed by epsilon 0. Then we could write E into integral of ds, that is equal to Q enclosed by epsilon 0. E is written as E itself. Integral of ds, now it should be the radius of the Gaussian surface, and if it is on the surface means we have to take the Gaussian surface also as a sphere of radius capital R. The Gaussian surface in this case should be taken as a sphere of radius capital R. Therefore, E into 4 pi capital R square is equal to, what is Q enclosed? If you are taking Gaussian surface, it's the radius of capital R, then Q enclosed is Q itself. Q enclosed in this situation is Q itself, therefore Q by epsilon 0. And we will get the equation as E is equal to, we are taking this term to the side, and if we are rearranging, we could write 1 by 4 pi epsilon 0 Q by capital R square. This is the electric field intensity on the surface. Electric field intensity on the surface. We are getting an equation like this. And if we are going for an equation, electric field intensity outside. Let me write. For electric field intensity outside the conducting sphere, we will have to consider a Gaussian surface like this. Then let us say, in this case also, the radius of the Gaussian surface, let us assume it as small r itself, and in this case we will write integral of E dot ds, that is equal to Q enclosed by epsilon 0 E into integral of ds, that is equal to Q enclosed by epsilon 0. In this case, E into integral of ds, it should be what? 4 pi small r square. In this case, small r should be the distance from center to this point. Okay. In the outside region, this is regarded as small r. This is regarded as small r. Q enclosed will be Q itself. Since the total charge enclosed by this blue dotted sphere, it should be Q itself, therefore Q by epsilon 0, and we will get E is equal to 1 by 4 pi epsilon 0 Q by small r square. This is the formula for E outside. Okay, this is the third formula, and we could define the three formulas in terms of charge density also. That is, as we know, volume charge density rho, it is 3q divided by 4 pi rq. Therefore, from this term, let me write what is q by 4 pi. If I am retaining this q by 4 pi at one side, then we will get q by 4 pi is equal to rho capital R cube divided by what? Rho capital R cube divided by 3. Is it clear? Then if I am substituting for this q by 4 pi in this, we will get electric field intensity inside. The remaining term other than q by 4 pi, it is r by epsilon 0 r cube. Then instead of this q by 4 pi, we will have to substitute rho r cube divided by 3. Therefore, we will have an r cube over here and an r square over here. They will get cancelled and there should be an r in this region. Therefore, electric field intensity inside, it can be written as rho r divided by what? 3 epsilon 0 capital R. This is one expression, another expression for electric field intensity inside. Then electric field intensity outside, this could be also rearranged by substituting q by 4 pi as rho r cube by 3. Therefore, remaining is 1 by epsilon 0 small r square into, instead of this q by 4 pi, we could write rho r cube divided by 3. Then ultimately we are getting rho r cube divided by 3 epsilon 0 small r square. This is the expression for electric field intensity outside. And if we are speaking about electric field intensity on the surface, let's say q by 4 pi, it could be replaced as rho r cube. Therefore, electric field intensity on the surface, it will be 1 by epsilon 0 r square into rho r cube by 3. Then we could cancel this r cube and r square will get cancelled. R square and r cube will get cancelled. There is an r over the numerator. Therefore, electric field intensity on the surface will become rho r. There will be an r on the numerator, rho r divided by 3 epsilon 0. Okay. Therefore, these are the formulas. Then let me compare it. There is one correction in this derivation, that is r cube and r cube are getting cancelled. Means if we are getting cancelling this r cube and r cube means there won't be a r. It was a mistake. Therefore, electric field intensity inside it should be rho r divided by 3 epsilon 0. Let us summarize. Electric field intensity inside the Gaussian surface is having one formula of 1 by 4 pi epsilon 0 qr divided by r cube, where small r is the distance from center to inside point and capital R is the radius of this non-conducting solid sphere. The other formula is rho r divided by 3 epsilon 0. This is the next formula. Electric field intensity outside the non-conducting solid sphere, it should be 1 by 4 pi epsilon 0 q by small r square, and the other formula is rho r cube divided by 3 epsilon 0 r square. These are the two formulas for electric field intensity outside the sphere. Then electric field intensity on the surface of the sphere, it is also having two formulas. Electric field intensity on the surface is 1 by 4 pi epsilon 0 q divided by capital R square, and in terms of volume charge density it will be electric field intensity on the surface will be rho r divided by 3 epsilon 0. Rho r divided by 3 epsilon 0. Hope you have understood this. Memorize these formulas. Okay.